Yogah Karmasu Kaushalam.
Good morning, friends. A very warm good morning to all the participants of this refresher course. At the outset, I would like to congratulate Professor P.N. Gajjar, Head of the Department, Gujarat University, Physics Department, Gujarat University, Dr. A.M. Vora, Associate Professor, Physics Department, Gujarat University, who are the coordinators for this course. And they have taken pains to organize this second online refresher course in physics under the UGC Human Resource Center of Gujarat University. So I welcome all the participants to this participants of this online refresher course, and I am very happy to be interacting with all of you. And I would like to thank Professor Gajjar and Professor Vora for giving me an opportunity to share my views on the topic of quantum mechanics, or the origin of quantum mechanics. Friends, as you all know, quantum theory is unique in the history of science and intellectual history of man. In its conception, it made a complete break with the past and fashioned a new worldview about the structure of matter and radiation and many of the fundamental forces of nature. It brought in a paradigm shift in our understanding of nature, and therefore I thought of sharing the story of the origin of quantum as my topic of today's talk. I hope that I'll be able to, convince you about the wonderful story, or rather, you would love to hear this wonderful story. And in my experience as a teacher for more than 25 years, I have observed that we seldom teach history of science while delivering our lectures on a regular basis. I know we are under lots of constraints of time, with the semester system being squeezed to maybe 2 months, 2.5 months, 1.5 months, and so on and so forth. So at times I know that conditions are not in our control, but I firmly believe that if we can share the excitement, the beauty of the development of scientific ideas, the history behind development of scientific ideas, then we can make our lectures more interesting. At the same time, we will in fact demonstrate to the students how science works, how these scientists think, how our scientific ideas evolve with time. And since we are teaching to the students of science, to develop this scientific attitude amongst the students is one of the primary tasks for us. And I'm sure if we can share the excitement of discoveries of science with the students, then we will be able to arouse interest amongst the students as far as physics is concerned. So with this, background, with this idea, I decided to share the story of genesis of quantum by means the you can say quantum, which was discovered by none other than Max Planck. So today I am going to, share this wonderful story, and I hope at the end of this lecture you will be also fascinated by this story. Many of you may have known this, many of you may not have known this, but I believe we should teach history of science, or discuss history of science with students in our regular course delivery. So friends, the title of my talk for today is The Genesis of Quantum, and the hero of the story is none other than Max Planck. I start with a beautiful quote by Robert Oppenheimer in his book on Einstein, 100 Years of Relativity. Oppenheimer says it is not too soon to start to dispel the clouds of myth and to see the great mountain peak that these clouds hide. As always, the myth has its charms, but the truth is far more beautiful. I believe that this quote is befitting to the story that I am going to narrate today. The truth is far more beautiful. Way back in 1900, people believed that we had all the tools in our hand to understand nature at large. For example, we had the laws of motion, Newtonian laws of motion. We knew well about Newtonian mechanics, laws of gravitation, electromagnetic theory was well known, thermodynamics was established. So scientists at that time felt that we have the necessary tools, and with the help of it, we have discovered all the necessary tools to understand nature. And then there is nothing new left, new challenges left for us. So this is the famous statement by Lord Kelvin in the year 1900. There is nothing new to be discovered in physics now. All that remains is more and more precise measurement. So Lord Kelvin believed that as time progresses, we will be able to develop more and more accurate and precise instruments. So that will add to the preciseness of the measurement rather than anything new required to explain nature. So this was something which was professed by Kelvin in the year 1900. And as we all know today, Kelvin was wrong. So that starts, this is the background which starts, is the starting point of this wonderful story. The year 1900 and later on saw the collapse of classical physics. The physics which was developed by Newton since the time of Newton till 1900, and we all know that the causes for the collapse of classical physics was primarily the black body radiation, or you can say the ultraviolet catastrophe, the theory of relativity which could explain photoelectric effect, and both these observations, photoelectric effect and black body radiation, they were connected to light. Now these two phenomena primarily were responsible for the collapse of classical physics. If you look at the 20th century, we had some major advances of 20th century. One of them, of course, is the special theory of relativity developed by Einstein in 1905, general theory of relativity, which was followed up in 1915, and of course, the quantum theory and quantum mechanics, which took nearly 27 years for it to be developed into a full-fledged theory. So going back to the year before 1900, so classical physicist view. So in classical physics, matter was assumed to be continuous. So discreteness of matter and energy was something which was, in fact, I should say, in classical mechanics, energy was assumed to be continuous. And everything people believed can be explained with the help of, energy and transfer of energy from one body to another. So right in the mid 18th century and later, there were atomists, chiefly Boltzmann and Maxwell, who argued that matter was not continuous, but in fact it is made up of discrete atoms and molecules. Not only did they believe in the existence of atoms or molecules, they went beyond that. They said the thermodynamical properties of material substance can be calculated from the mechanical motions of atoms or molecules using statistics. So they applied statistics to calculate the thermodynamical properties, and they could connect the thermodynamical properties of substances to the mechanical motions of their constituents which were atoms or molecules. Now, this was the view which was prevalent at that time. And in this background, we will be discussing the revolution which was brought about by Planck. Planck himself was a typical classical physicist, and he was, not antithetical, or he was not in favor of the ideas of Maxwell and Boltzmann. So Boltzmann provided the statistical interpretation of second law of thermodynamics, as you all know. He interpreted entropy uh, statistically, and this particular interpretation of Boltzmann of the second law of thermodynamics was something which Planck did not, or rather disagreed, and this topic of second law of thermodynamics was Planck's doctoral thesis, and Planck prided himself to be the one who has understood the second law of thermodynamics uh, well. So Planck believed that his way of looking at second law of thermodynamics was correct view, and he was not he disagreed with the statistical interpretation. So he believed that second law of thermodynamics is absolute, while Planck said that it is statistically correct. So this was the disagreement between Boltzmann and Planck. So Planck regarded this atomic, as I said, atomic hypothesis as a dangerous enemy of progress, you see, which would ultimately have to be abandoned in the favor of assumption of continuous matter. Planck, being classical physicist, he believed that this atomic hypothesis, the dangerous enemy of progress. And you will find later on in the talk that Planck completely changed his viewpoint, and in fact he acquiesces to this idea of atomic hypothesis as time progresses. So Planck himself, as I told, disliked Boltzmann's interpretation, and he set out to refute it. So he wanted to prove Boltzmann wrong, and he chose the problem of black body radiation to settle scores with Boltzmann. So why black body radiation? Then the physics of cavity radiation appeared to have no connection with atoms and molecules, something which Planck did not believe in. It was a problem of continuous wave. So you have, in a black body, you have an electromagnetic radiation, and this electromagnetic radiation can be explained, or can be understood with the help of Maxwell's equations. Wave is a continuous phenomena, or electromagnetic wave is continuous. Maxwell's equation describe this wave, and this wave interacts with the walls of the container, and ultimately what is going to happen is the second law of thermodynamics is going to drive the radiation to equilibrium. So this was the problem, or problem of black body radiation, where an electromagnetic radiation is interacting with the walls of the container. Planck believed that if he could show how equilibrium is reached, so idea of Planck was, if you can show how this black body radiation or black body reaches equilibrium, and that too without resorting to any statistical arguments. If you can do that, then he could undermine the very basis of the mechanical description which was propounded by atomists like Maxwell and Boltzmann. So he wanted to show or explain how the black body radiation reaches equilibrium without resorting to statistical arguments which were used by Maxwell and Boltzmann. So thus began. So this was the starting point for Planck to attack, to study the problem of black body radiation, and ultimately his acquiescence to the atomic hypothesis. So we'll begin at the beginning. So this problem of black body radiation has its origin in the year 1859. 1859 was a watershed year in the history of science. There occurred a number of events which were to change the course of science. One such event is the observation by Leverrier in the year 1859 12th September, when he writes a letter to Hervey Faye and presents it to the French Academy, where he observes that the perihelion of Mercury advances as it revolves round the sun. Now, this was the first sign. And see, this advancement of perihelion could not be explained using Newtonian mechanics. So, this advancement of perihelion was the first sign or signal that Newtonian mechanics was inadequate, and a new improved theory is necessary to explain this remarkable and strange observation. So that's how 1859 is important. Then another watershed event which occurred in 1859 was the publication of the famous, one of the most famous books which ushered in the revolution as far as the evolution of species is concerned. So that was Charles Darwin book on the origin of species by means of natural selection. So that was also published on 24th November 1859. In the meantime, in October 1859, it was Gustav Kirchoff, a German physicist, who proved a very, very important result while studying the problem of heat radiation. What was it? If radiation and material bodies are in equilibrium at common absolute temperature T, then the energy density of the radiation per unit frequency interval is a universal function of frequency and temperature, independent of the particular material bodies present. So this was something extraordinary which was discovered by Kirchoff. See, what he says is that energy density of radiation emitted by any body per unit frequency interval is a universal frequency, a universal function. So universal function means it's independent of any material body, shape, size, and everything. So this Kirchoff discovered this universal character of this radiation law, and in that triggered a scientific revolution, in my opinion. That triggered the quest to understand the black body radiation, which ultimately resulted in Planck discovering the quanta, or propounding the idea of quanta. So according to Kirchoff, see, this spectral density is a universal function. So what is spectral density? It's the energy of radiation per unit volume of the black body in the frequency range nu and nu plus delta nu at temperature T. So it's a universal function of nu and T. And he exhorted that one of the primary aims of science should be to find out this universal function, that is spectral density. It is highly important task, in his opinion, in his words, Kirchoff's word, it is highly important task to find this function rho. Great difficulties stand in the way of its experimental determination. Nevertheless, there appear grounds for the hope that it can be determined by experiment, since undoubtedly it has a simple form, as do all functions which do not depend on the properties of individual bodies, and which has become acquainted with till now. So since it was a universal function independent of the properties of the body, it must be simple and must be found out. This was Kirchoff's exhortation. So the challenge was to determine the spectral density. So in order to find out, there were a number of problems which were faced by experimentalists at that time, around 1859. So first problem was to construct perfectly black bodies. Then to devise radiation detectors with adequate sensitivity. And third, to find out ways to extend the measurements over large wavelength domain. So these were the problems. See, we did not have the technology to have very accurate or sensitive radiation detectors over wide wavelength range. So that was the challenge. So it took nearly 40 years of painstaking efforts by experimentalists until sufficient data was gathered to answer Kirchoff's question. So from 1859, it took us nearly 40 years to come up with an answer to the problem or to the exhortation, Kirchoff's exhortation. So it was around 1896. One of the famous physicists, Wilhelm Wein, on the basis of thermodynamics and electromagnetic theory, he derived the form of the law which he believed governs the radiation emitted by a heated body. So this is Wein's exponential law, and it has an exponential character, e raised to minus b. So a and b are the constants which need to be determined. So this was derived by Wilhelm Wein. So the Wein's exponential law, it matched well with experimental results. And these experimental results were obtained by Paschen in the high frequency limit. These were the wavelengths, of course. So for his discoveries regarding the laws governing the radiation of heat, Wien was awarded Nobel Prize in Physics in the year 1911. So first step in understanding the law which governs the radiation emitted by a black body was taken by Wiens, and his contribution was ultimately recognized by the Nobel Committee. Simultaneously, around 1887, Imperial Physical Technical Institute, PTR, was established in Berlin, and it was the state of art laboratory, scientific laboratory at that time. And see, the aim for this laboratory was to develop energy efficient lights or bulbs. So energy efficient means it's the radiation which is coming out from a material. So they developed at PTR by mid 1890s, they developed very sensitive photometric and bolometric methods. So photometers and bolometers were developed, which could accurately measure the radiation coming out from a black body over a wide range of temperatures. So on one side, it was Wien who, uh, derived an expression for the spectral density, and it was accompanied by improved experimental techniques which helped in verification of Wien's law, and ultimately to the which led Planck to discover his revolutionary idea. Around 1899, so that was in 3rd November 1899, at a meeting of German Physical Society, these two great experimentalists, Lumer and Pringsheim, who were working at PTR, they presented some interesting findings. So they found, or they showed that Wien's law is obeyed at high frequencies, and they had observed deviations at low frequencies. So Wien's law seemed to be working well at high frequencies, but at low frequencies, they observed deviation from Wien's law. See, this was in 1899. So since Wien proposed his exponential law, it was nearly in 3 years or 2 years, people started observing deviations at low frequencies. I must say that these deviations, were, to a great extent, it was due to the, untiring, tireless rather efforts of Lumer and Pringsheim. And there were others such as Rubin, who was another person who was working at PTR. So it was realized that Wien's law was not valid at all frequencies. But before that, on 7th October, see, Rubens pays visit to Planck. Rubens was someone who was working at PTR, and at that time, there was this tradition of scientists going to each other's home during the weekend. So on one such Sunday afternoon, Rubens paid visit to Planck. And during the discussion, Rubens told Planck that the recent experiments have shown that the spectral energy density function follows what was called Rayleigh-Jean's law, and it conclusively proved that Wien's law was not valid at low frequencies. So this came as a shock to Planck. Why? Because Wien's law, I'll show it later on in the discussion, was in accordance with second law of thermodynamics. It followed, Planck knew that second law of thermodynamics is correct, and Wien's law, he could explain Wien's law from second law of thermodynamics. Now, once you say that Wien's law is not valid at low frequencies, it means it is putting some question mark regarding the validity of second law itself, which Planck was not ready to accept. So when Rubens told him that Wien's law does not obey or is not valid at low frequencies, Planck took it extremely seriously. So this is the Rayleigh-Jean's law, and the spectral energy density function is proportional to temperature at low frequencies. This was something which Rubens told Planck. So it means that Planck realized that spectral density function seems to have two limits. One is, of course, the high frequency limit, or you can say Wien's limit, where it is an exponential function. And for low frequency, it is Rayleigh-Jean's limit. So Planck realized that spectral density seems to vary between these two extremes. So his task was to find out a spectral density function which is valid at all the frequencies. So somehow he has to find out a formula which approximates Wien's formula at high frequencies and Rayleigh-Jean's formula at low frequency. So this was something Planck realized that he needed to ultimately address this problem and solve it. So in 1897, Planck was by that time 40 years old. So this problem of black body radiation became the center point of his life during those years of late 1890s. So Planck was, especially as I told you earlier, he was attracted to this problem of black body radiation because it has a connection with thermodynamics, and Planck had a fascination with something which is absolute and universal, as suggested or as exhorted by Kirchoff. The spectral energy density function seems to have a universal character. So this was something which Planck found uh, quite Planck was attracted to, and that's why he decided to attack this problem of black body radiation. So this is what Planck said later. The spectral distribution of radiation then represents something absolute. And since I had always regarded the search for the absolute as the loftiest goals of all scientific activity, I eagerly set to work. So Planck got extremely interested in the problem of black body radiation. So in order to derive the formula for black body radiation, Planck had to simulate the black body. So he said that the best way to simulate a black body is to assume that the black body is made up of an ensemble of Hertzian electromagnetic oscillators. And he said why they should be Hertzian electromagnetic oscillators, because the spectral density distribution function itself is universal and is independent of material of the body. So why not take the simplest of oscillators which were well studied at that time? And he believed that having assumed them to be oscillators, the derivation of the formula for black body radiation can be calculated, or it can be derived easily. So these were the considerations for Planck to assume that the material of the black body is made up of Hertzian electromagnetic oscillators. So in June 1899, Planck derived the relation between spectral energy density function and the mean energy of the oscillators. So he found out that rho is a function of the mean energy U, and he says that the next problem, of course, is to find out U. If you can work out the value of average energy U, then you will immediately find the spectrum of black body radiation. Okay, so this is something which Planck believed in, finding out the average energy of these Hertzian oscillators. So once you do that, he believed that I will get the spectrum for black body radiation. So naturally, for him, the next step was to find out the relation between E, T, and nu, or you can say the average energy of the mean energy or the average energy of the oscillators. But the twist in the story is what Planck did not do next. This is interesting. As I told you earlier, Planck was, in fact, not happy with the statistical thermodynamics propounded by Boltzmann. So he did not like this classical statistical mechanics. And classical statistical mechanics predicted or derived, said that at equilibrium, each degree of freedom will have energy half kT. So this is the famous equipartition theorem. Now, so the mean energy of harmonic oscillator, which has 2 degrees of freedom, will be equal to kT. And if you directly substitute U is equal to kT, then you arrive at Rayleigh-Jean's law. Since Planck did not agree with classical statistical mechanics, he did not take this obvious approach. Instead, he tried and to attack the problem from the point of view of thermodynamics. This formula, Rayleigh-Jeans, as we all know, had this problem that as frequency goes on increasing, then the spectral density becomes infinite, and it was so this is what is called the ultraviolet catastrophe. So this Rayleigh-Jeans formula did not have anything. It did not have anything there is no peak as far as frequency is concerned, and you find that the spectral density becomes infinite, leading to the ultraviolet catastrophe. So this, had Planck followed classical statistical mechanics, he would have arrived at Rayleigh-Jean's law. But then Planck precisely did not do that. So why did Planck did not make this substitution? As I told you, Planck did not like the atomist view. He was unhappy with Boltzmann's statistical mechanics, which correlated energy with temperature. So this is something which Planck did not like. So that's why he did not substitute U is equal to kT in the expression. So he attacked the problem from the side of thermodynamics. Why thermodynamics? Because it was his home territory. He had his PhD in the on second law of thermodynamics, and he felt himself to be on a safer ground. So he attacked the problem from the side of thermodynamics. So instead of trying to find out the dependence of intensity of radiation on temperature, which is what classical statistical mechanics did, he tried to correlate the intensity with the entropy of the radiation. So rather than temperature, he said, let me correlate the energy, let me correlate the intensity of the radiation with entropy of. So this is one of the, you can say, a different approach or path which was taken by Planck, and this crucial step, in fact, led to the discovery of quanta, or idea of quanta. So what Planck did, he defined entropy of Hertzian oscillator using this formula, and using the relation 1 upon T is equal to ds by du, So S is equal to minus u upon b nu ln u upon alpha nu. So using the relation 1 upon T, so this is a simple mathematical calculation. And on integrating this equation with the condition that S is equal to 0 when u is equal to 0, we find that takes this form, and the second derivative of S with respect to u, so S is entropy and u is the mean energy. He found out a quantity which is called, which in this case I am calling it as R, and he realizes that R is nothing but inverse of second derivative of entropy with respect to mean energy, and that becomes proportional to U. So Planck realized that in the Wien's regime, the regime where, second law of thermodynamics in Planck's opinion worked well, in that case, this R was proportional to the mean energy of the Hertzian oscillator. So, as I said, Wien's law is entirely consistent with second law of thermodynamics. This is what Planck believed, and this is what he found also. But then at lower frequencies, where Wien's law is not valid, so that was the region of concern as far as Planck was. That was a region of, you can say, a regime which is, you can say, Rayleigh-Jeans regime. It was the matter of contention as far as Planck was concerned. So to obtain the dependence on temperature at low frequency, now Planck is trying to attack the problem from low frequencies, at low frequency or in the low frequency regime. So Planck supposed that let u be equal to alpha t, or it let u be proportional to t, because he knew that at lower frequencies it was the Rayleigh-Jeans formula which worked out well. So in that case, he realized that this quantity R was proportional to u square. So what Planck realized is that this value R becomes proportional to u in the Wien's regime or higher frequency regime, and in the Rayleigh-Jeans regime at low frequency, R becomes proportional to u square. So what was necessary for Planck was to interpolate, because each proportional to u was working well in Wien's regime, proportional to u square was working well in Rayleigh-Jeans regime. So he need to interpolate these two extremes to get the correct formula. So one obvious thing that he could do was to add the two. So minus b nu u, the first term, is the Wien's regime, and the second term is the Rayleigh-Jeans regime. And on integrating using the boundary conditions, he found out that I think it should have been rho t. So the spectral energy density rho nu t assumes this form alpha b nu exponential b nu by t minus 1. So in the Wien's limit, he obtained the relationship between the new constants, and ultimately he expressed the formula, which is, we all know, the famous Planck's radiation, black body radiation formula. So he ultimately arrived at at his famous radiation formula using a route which is uh, other than, you can say, using another route, trying to avoid the classical statistical mechanics approach followed by Boltzmann. But the equation that he found out, or you can say he suggested, this expression for entropy, S is equal to minus U. So this expression for entropy was something that he calculated backwards from the final answer. So he knew the answer, and to get that answer, what should be the expression for entropy? So he made a reverse calculation and said that let me express entropy. So if I express entropy of the Hertzian oscillator in this particular form, then I will be able to get the correct formula for the black body radiation. So this is the formula which he ultimately derived, and he presented this new black body radiation formula at the German Physical Society meeting at Berlin on 14th October 1900, which we call it as the birth date of quantum theory. So quantum theory was born on 14th October 1900, the day when Planck presented this radiation formula. So once he presented, the very next morning I received a visit from colleague Rubens. He came to tell me, this is what Planck says, he came to tell me that after the conclusion of the meeting, he had that very night checked my formula against the results of his measurements and found a satisfactory concordance at every point. Later measurements too confirmed my radiation formula again and again. The finer the methods of measurements used, the more accurate the formula was found to be. So he found that Rubens told him that his formula matched quite well with the measurements that he had carried out over a period of time. So it was valid for all the frequencies or over the entire wavelength range. The Planck's formula was observed to match well with the experimental results. Max Jammer, in his famous book, writes, never in the history of physics was there such an inconspicuous mathematical interpolation with such far-reaching physical and philosophical consequences. So the mathematical interpolation which was brought about or brought in by Planck was just to get the correct formula. He wanted to get the correct formula. He knew how the formula reduces to what in the two extremes. In the Wein's regime, R becomes proportional to U. In the Rayleigh-Jeans regime, R becomes proportional to U square. So he just interpolated. But boy, oh boy, what great interpolation that he could carry out, and it has such far-reaching physical and philosophical consequences. Abraham Pace, in his book on Einstein, writes, had Planck stopped here, so that means at this point where he got the correct formula, he would have always be remembered as the man who found the radiation formula. So if Planck did not go further beyond that, he would have been remembered just as if an ordinary scientist who has discovered the correct radiation formula and would have not ordinary, but would have a place amongst the greats. The fact that he went on to supply a theoretical support for his formula is a measure of its greatness. So he would have been just another scientist, or maybe one of the great scientists for having discovered the radiation formula. But Planck went beyond that. He tried to derive, he knew that the way he arrived at the formula was not theoretically correct. He did not do it from fundamental first principles of physics. Now, so it was his ad hoc assumption of the entropy, dependence of entropy on U, which resulted in the correct formula. He mathematically interpolated the formula between the two extremes, and that's why he knew that although he got the correct radiation formula, it was on a sticky theoretical grounds. He was not on he was on a sticky ground. He was the way he derived it, he was unhappy. It was not from first principles, and that's why he says that. But even if the absolute validity of radiation formula is taken for granted, so long as it had merely the standing of a law disclosed by lucky intuition, it could not be expected to possess more than a formal significance. For this reason, this is what Planck says, on the very day when I formulated this law, I began to devote myself to the task of investing it with a true physical meaning. This quest, as a matter of course, led me to led me to study the interpolation of entropy and probability. In other words, to pursue the line of thought inaugurated by Boltzmann. He realized, see, this is very crucial. Planck realized that the way he arrived at the formula was not from the first principles, was not correct. It was an ad hoc assumption on his part, and he tried to do he used this ad hoc assumption merely to avoid using classical statistical mechanics. Now he realized that, see, his derivation was in so to say, not on a sound theoretical background. So avoiding classical statistical mechanics did not lead him to the correct method of derivation of the formula. So now if he wants to rederive it from the first principles, he knew he had to resort to the classical statistical mechanics of Boltzmann. So if you see, Planck initially started with his dislike for classical statistical mechanics, but then this observed results of black body radiation forced him, okay, to accept the approach, Boltzmann's approach, and thus converting him into an atomist. So Planck takes the route of statistical mechanics, which was, propounded, or you can say it was extensively used by Boltzmann. So he interpreted second law statistically, and Boltzmann established connection between entropy and probability. So what Boltzmann did, Boltzmann introduced a relation between entropy and the number of microscopic configurations or complexions, as he called it, of the molecules. So the number of microscopic configurations which were available to a molecular gas under certain constraints. Boltzmann said that the entropy of the molecular gas was proportional. It was dependent on the number of microscopic configurations of the gas. Larger the microscopic configurations, more will be the entropy. Another thing which Boltzmann said was, at equilibrium, the microscopic configuration will be maximum, subject to the constraints that n is fixed and the energy of the molecular gas is fixed. So Boltzmann defined the state of equilibrium as the state where the gas has maximum microscopic configuration. According to Boltzmann, one needs to calculate the number of possible complexions or configurations, microscopic configurations, and he, in order to do that, because in order to determine omega, Boltzmann assumed that the energy of the molecules of the gas is discrete. So that means he said that if gas is made up of n molecules, then the total energy of the gas will be equal to n times epsilon, where epsilon is the minimum energy of the molecules of gas. So in other words, Boltzmann, in fact, you can say quantized, it tried to take a packet of energy, which is epsilon. But when he derived, finally, during the derivation, he took the limit epsilon tends to 0 to arrive at the formula for entropy in terms of number of microscopic configuration. So the famous formula S is equal to K ln omega was derived in the limit epsilon tends to 0. So in that sense, you can say Boltzmann also continued with the continuous continuous nature of energy, because his derivation involved epsilon tends to 0. So this was Boltzmann's method. So Planck resorted to this method, and let us see what he did. So Planck's method, once again, Planck was he wanted to determine omega. So what he said, or what he considered, suppose the black body is made up of n oscillators, all of frequency nu, then the total energy un will be given times un will be given by n times u. Now entropy being an additive function, Sn will be entropy of the gas will be equal to n times entropy of the oscillators, total entropy will be equal to n times S. The entropy of the n oscillator Sn is given by Sn is equal to K ln omega, which is Boltzmann's formula. So Planck considered once again discrete elements. So the oscillators or energy of the oscillators, he assumed once again to be discrete, just like Boltzmann, so that the total energy is given by P times E. Till this point, his approach is exactly same as Boltzmann. But what, as I told you, what Boltzmann did, he ultimately he arrived at the expression under the assumption epsilon tends to 0. In this particular case, Planck also tried to derive the expression for to arrive at the expression for Planck's blackbody radiation law, or Planck's law, and he tried to adapt the same approach which was taken by. He took the same approach which was adopted by Boltzmann, that is epsilon tends to 0. Planck tried to do that. So Planck worked out on the total number of ways in which p energy elements can be distributed over n oscillators. So the number of complexions will be equal to number of ways in which this can be done. I'll not go into details of the derivation, but the point is, since n is large and p is large for a given black body, so he used the Stirling's approximation and he found out the expression for S. So this was S means entropy of a single Hertzian oscillator. And since S, which was function of nu and u, and K was a universal constant, Planck realized that the dependence or the frequency dependence of entropy should come through nu, because S was function of nu and u. Now, if you look at this expression, S is function of k, 1 plus u upon epsilon. So it's function of k, u and epsilon. So k being universal constant, u was the average energy he knew. So the frequency dependence of entropy must come through epsilon. This was the realization of Planck. So he took the energy epsilon is equal to, once again, proportional to nu. That proportionality constant was called h. So this Planck's innocent looking formula, it sparked the second great revolution of 20th century, quantum mechanics. So for the first time, energy was assumed to be proportional to frequency. Classical electromagnetic theory says that the energy or intensity is proportional to square of the amplitude. Now here is a paradigm shift. From square of the amplitude, we say that the energy is proportional to frequency. So that ushered in a revolution. So from the expression Planck found out rho is equal to, so he substituted, he found out u and he substituted the value of u and he arrived at this correct formula, which is called the Planck's law. So, as I told you, Planck also tried to arrive at this formula assuming epsilon tends to 0, the way Boltzmann did. But to his utter surprise, to his great surprise, Planck could not arrive at the formula under the assumption epsilon tends to 0. So epsilon tends to 0 meant that the energy is continuous, while epsilon not equal to 0 meant that the energy is quantized. So Planck, being a classical physicist, he was not very happy assuming epsilon is equal to h nu. So what do you find from Planck's law? Planck's radiation law contains three fundamental constants: speed of light, Boltzmann constant, and Planck's constant. So which makes its maiden entry for the first time into physics jargon. So first time H was introduced in the physics jargon by Planck, and he believed that his constant is nothing but mere calculational contrivance. See, it's just for getting the correct formula. He says I am using epsilon is equal to h nu, but ultimately the energy or the wave or electromagnetic wave is still continuous, and it is only when the energy is absorbed by walls of the container, this discreteness or the quantization of energy is required. So he said it is the process of emission absorption of light by cavity where you take epsilon is equal to h nu, but it did not apply to the fundamental nature of light itself. So light itself can be described, he said, very well by the Maxwell's equations, and this discreteness in energy is not fundamental in nature. This is what Planck believed after deriving his Planck's law. So according to Planck, EM radiation is still classical, only energy exchange is in packets. So this is what Planck believed. So Planck recalled in 1931 his act of desperation. He said it was an act of desperation. I had to obtain a positive result under any circumstances and whatever cost. So since he wanted to get the correct results, correct formula, as an act of desperation, he took epsilon is equal to h nu. He considered that energy is made up of packets. Energy is discrete, and that was an act of desperation. So what Abraham Pace writes, his reasoning was mad, Planck's reasoning, but his madness has that divine quality that only the greatest transitional figures can bring to science. It cast Planck, conservative by inclination into the role of a reluctant revolutionary. So Planck, being a typical classical physicist, got transformed, or you can say metamorphosis of Planck took place. He became a reluctant revolutionary. He ushered in a revolution that energy content or energy exchange is in the form of packets. It's exchanged discretely, something which was against the believed concept or something which was accepted for more than 200 years. So he did it, but he did it reluctantly. He did not embrace this idea, with whole heart. Somewhere down in his heart, he believed that he should be able to, get to the correct formula of black body radiation without introducing energy quanta. And this revolution, this idea of Planck, it changed everything in physics and chemistry. But the problem is, himself did not realize it, that he has ushered in a revolution. Why? Because he still continued to believe that he will be able to somehow circumvent this idea of epsilon proportional to frequency to arrive at the correct formula. So next 10 years, 1 decade of his life, Planck devoted to, he put in extensive efforts to derive the formula for black body radiation without using the assumption epsilon is equal to h nu. And as we all know, he failed in doing that. And finally, he accepted it, that this is how the nature is. So the discreteness, the graininess present in the energy was reluctantly accepted by Planck. So what it did, it failed to alert the physics community about the storm ahead. So it ushered in a revolution which hardly anyone at that time could foresee. In fact, I can say no one could foresee, including Planck. So this was the story. This is how science, gets developed, how ideas of people evolved, even scientists, how their own ideas change with time, how Planck, in fact, from you can say a classical physicist or a kind of an energetist who believed in continuous exchange of energy, he ultimately adopts, transforms, accepts the atomist view, something where he initially started with dislike for classical statistical mechanics. He adopts that. So see, this is how, ideas evolved. This is how scientists, their own ideas evolve, how it changes, the role of experiment in deciding, in guiding the theorists to arrive at the right radiation formula. So these are, some of the, uh, I think, the ideas which we need to share with our students for them to realize how role of, theorists and experimentalists, when they work in tandem, how we can unravel, how you can understand the mysteries of universe, of nature. So I finally conclude, the radical introduction of quantum of action as an act of desperation catapulted Planck into being a reluctant revolutionary, which in my opinion is an appropriate aphorism used for Planck. And the quantum theory owes its origin to Planck's profound insight into thermodynamics. So these are the references from which I had prepared this talk. So I would like to once again thank Professor Gajjar and Professor Vora for giving me an opportunity to share my ideas with the participants. Thank you.